So some isotopes are radioisotopes. Some are stable isotopes. Okay, all it means by a radioisotope is that something is unstable about the nucleus. So it's going to give off particles or energy or a combination of both so that that nucleus becomes more stable. Okay? And it will keep decaying until it forms a stable arrangement. Okay, until that nucleus forms a stable arrangement. And when that decay occurs, it sometimes turns into a whole new element. Okay, so because the particles that it gives off may include protons in the particle. Okay, and if it includes protons, that means it'll change its atomic number and it'll turn into a whole new element. Okay. Other times when it decays, it's still the same element, but it might change its mass number, or it just might change its arrangement a little bit or something like that. So there's three common types of radioactivity. There's a lot more than these three types. I'm just going over three common types, okay? And then we're going to do an activity with these. So one type of radioactivity, or one common type, is alpha decay. And what this means is that from the nucleus of this isotope, it'll give off 2 protons and 2 neutrons. It's equivalent to 2 protons and 2 neutrons. And this we already talked about with Rutherford's experiment. Remember, he aimed alpha particles at the gold foil. He knew that the alpha particles were positively charged because if it's 2 protons and 2 neutrons, the overall charge is positive too, right? And then that's how he determined that the nucleus must be positive, because if these alpha particles are deflected away from the nucleus, like charges repel. Okay? It's often represented as a helium nucleus. Okay, it's equivalent to a helium's nucleus, but the helium is atomic number 2. And the most common isotope of helium has 2 protons and 2 neutrons. Okay, so it's equivalent to a helium nucleus. So a lot of times we represent it as a helium nucleus. But I want you to keep in mind that an alpha particle is not helium. It's just equivalent to a helium nucleus. So when you see this in nuclear equations, because we're going to write nuclear equations, when you see that in a nuclear equation, you got to remember that it's an alpha particle, which is equivalent to a helium nucleus. It's not like helium gas is escaping out of the element, because it doesn't have protons. In order to be a helium atom, it would also have to have 2 electrons. This is just equivalent to what a helium nucleus looks like. So that's how it's represented. I don't love that representation, but that's what you'll most commonly see. Or you might see it represented with the Greek letter alpha. Okay. And you might see the 4-2 there as well. Its mass number is 4 and its atomic number is 2. Remember this upper number is the mass number, that's your protons plus your neutrons. The bottom number is the atomic number, which is the number of protons. So this is protons plus neutrons. This is just protons. So the reason I don't like that is because it's not helium that's escaping, it's just equivalent to a helium. So an example of this would be like thorium-230. that's 90, I'm sorry. Right there. Thorium on the periodic table is TH. Okay, it's number 88 or number 90 on the periodic table. And one of the isotopes of thorium is thorium-230. There's lots of isotopes of thorium. But this is one that gives off an alpha particle. So just remember that He42 just represents an alpha particle. It's not really helium. Now, when I write any kind of chemical equation, in this case it's a nuclear equation, the arrow is kind of like an equals in math. So both sides have to add up to be the same thing. So if this has a mass number of 4 and the total mass is 230, what mass number is missing? What plus that 4 is going to give you 230? 227. And we have to do the same thing with the atomic number. What plus 2 is going to give you 90? Okay. So then to know what element it turned into, because since thorium gave up 2 protons, it's going to turn into a whole new element. If you look up on the periodic table, number 88 is down the bottom left up here on the periodic table. It's radium. And its symbol is Ra. It's the cheerleader of the periodic table. So radium is formed. So this one is referred to as the parent isotope. Okay, that's my parent isotope. What it decays into is called the daughter isotope. Right. So when you're talking about radiation, nuclear equations, there's only parents and daughters. There's no sons or fathers. Parent and daughters. Okay. Now that may or may not be stable. Okay, it's more stable than this isotope, but it still may be unstable. So that may actually also undergo decay and may give off another one. So that may then become your parent. If that's still unstable, then that'll become a parent, go through another step of radioactivity, form another element. Okay, that's a little bit more stable. And that keeps happening over and over until finally you reach a stable element. Okay. But that's an example of alpha decay. Another common type of radioactive decay is beta decay. So this is equivalent to an electron. Okay. But you might say, well, how does an electron come out of the nucleus? This is nuclear decay, right? It's the nucleus that's decaying. We know that in the nucleus, it's protons and neutrons, right? The electrons are outside the nucleus. So if this is nuclear decay, how do we give off something that's equivalent to an electron? What actually happens is a neutron decays. It's actually a neutron inside the nucleus is decaying. Okay, so think of a neutron. We know that a neutron is neutral, right? It has no charge. But remember we talked about quarks, that subatomic particles are actually made up of even smaller particles called quarks. So think of a neutron as being a proton fused to an electron. Okay, the quarks that make up a neutron are the quarks that make up a proton and an electron, all combined into one. So what happens is a neutron inside there actually decays and forms a proton and an electron. The proton stays in the nucleus. The electron is shot out of it. So what ends up happening is you have an extra proton now, right? Because a neutron turned into a proton. So that actually makes your atomic number go up because one of the neutrons in the nucleus turned into a proton. And it shot out what's equivalent to an electron. Okay. The mass number won't change because remember, mass number is protons plus neutrons. So if you simply converted a neutron into a proton, the overall number of protons plus neutrons is the same, right? One of your neutrons just turned into a proton. So your atomic number goes up by one, but your mass number stays the same. Okay. This is what happens in carbon-14. Remember we talked about carbon dating? So the isotope of carbon, carbon-14 is radioactive. Okay. It emits a beta particle because one of its neutrons turns into a proton and ejects an electron, what's equivalent to an electron. So I have to figure out which element that is. So what plus 0 gives me 14? 14. So remember we said the mass number is not going to change, right? Because you're just simply converting a neutron into a proton. So your overall protons plus neutrons is going to be the same. Okay. -1 plus what gives me 6? 7. Remember our atomic number goes up by that, right? And if you look on the periodic table, number 7 is nitrogen. So when carbon-14 decays or gives off beta decay, it actually turns into a very stable form of nitrogen. Questions on that? And then a third most common type that we're not going to do in the activity that we're doing today, a third most common form is gamma. But gamma is pure energy. Okay, so there's no particles involved, it's just high energy given off. The way that occurs is the nucleus just rearranges itself. So, you know, like sometimes you might get tired of the way your furniture is arranged in your living room, so you decide to rearrange it to get a better view of the TV or whatever. That's the nucleus. It doesn't like the way it's currently arranged. It doesn't like the way the protons and neutrons are positioned in there. So what happens is it just shifts them around, just jumbles around with protons and neutrons. And when it does that, it becomes more stable, so it gives off energy. It's just pure energy. If you ever see, I have trouble drawing alpha. That's, or I mean gamma. That's kind of what a gamma symbol looks like. Okay, kind of like a funny looking Y. Oh, and beta, I forgot. You might sometimes see beta look like that. It's kind of like a capital B with a tail. We're going to have to put that over here. More commonly, you'll see it as a looking like an electron, even though it's not an electron. It's part of the decay of the electron. But gamma, you might see it's kind of like a funny looking Y. If you'd see any mass number or atomic number on it, it would just be 0, 0. It's just pure energy. It's not. Everybody got that? All right. So we're going to do a little activity. I don't know if we'll get done or not today. But you're going to determine the decay series of uranium-238. Uranium-238 is the most common form of uranium, most common isotope. So I'm going to give you a deck of cards. You're going to start with uranium-238, okay? And you're going to keep this going through a decay series. You're going to keep decaying using alpha and beta cards, okay? Oops. The blue ones are alphas. They're represented by the helium-42 representing an alpha particle. And then the beta particles are represented with the yellow ones. They're your equivalent to an electron. And what you're going to do is you got to keep going until you use all of your cards. But you're going to start with uranium-238. And at the bottom, it says what the half-life is. You're not going to use the half-life, but just kind of look at them because they're all over the place. Like uranium has a half-life of 4.5 billion years. Okay. Others might have a half-life of a fraction of a second. So how fast they decay. Okay. They just decay at different speeds. But what you're going to do is you're going to get a piece of notebook paper. And you're going to start with the uranium-238. And you're going to decide, is it going to be beta radiation or alpha decay that's given off? Only one of those cards for the daughter, only one of those can be in. The correct daughter isotope will be. So you have to write two equations. You're going to say, okay, what am I going to get if it's alpha decay? What am I going to get? Well, what would be the mass number here? 234, right? Just make sure that they add up on both sides, right? This is like your equal signs. The 4 plus 234 is 238. And 2 plus what gives me 92? 90. You look on the periodic table, number 90 is thorium. Okay. Or is it going to be beta decay? Well, 0 plus 238 gives me 238, right? So my mass number is not going to change. And my atomic number has to go up by 1, right? Because 93 minus 1 gives me 92. So 93 is neptunium, I believe. So I look through my cards. Okay. I lay my uranium-238 down on my desk. Okay. I look through my cards to see which one of these, only one of these is going to be in my deck. It's either going to be thorium or neptunium. You have to be careful because here's a thorium, but it's 230. The mass number is 230. I need thorium with a mass number of 234, so that must be a different isotope. Oh, and I found one. It's thorium-234. Okay. Neptunium's not in my pile, so I know that that's not the correct one. So then on your sheet, you can just say, nope, X that one out. Okay. I'm going to lay down my alpha particle next to my uranium-238. And what it decayed into is my thorium-234. So I lay that down next. Okay. Now I'm going to do the same thing. This now becomes my parent. So I write that down here. because according to the card, thorium has a half-life of 24.1 days, which means it's going to decay. It has a half-life, it's going to decay. And I do the same thing. What do I get? An alpha particle, what do I get? A beta particle, find which one's in here, cross the one out that doesn't exist, and keep going until you finally get to a stable element. You'll use all of the colors. And your stable element is lead. Lead, one of the lead isotopes. Okay. So you'll need a piece of notebook paper. I have some back here. And you can either work with a partner or you can work alone. I don't care which way. I have a bunch of text. Yep. So just grab one of these. Just grab one of these. Yes. I'm sorry. I'm going to extend the deadline.
Oh, I think it.
And I just got started. The rest of it, we did the first one together. So I just got started. All right, I'm going to turn off my recording.